Welcome to St. Louis County Library's virtual program, Science in St. Louis, presented with the Academy of Science St. Louis. I'm so happy to be bringing these programs back. I know that I've really enjoyed doing them in person, and I'm just glad that we were able to get a few on our calendar. So thank you so much for being here tonight. Before we get started, I just have a few little tips and tricks when navigating our Zoom programs that I'd like to bring up. And also, I'm Denise Chappell. I'm the Adult Programming Specialist for St. Louis County Library. So going back to Zoom, you will notice when you move your cursor, different boxes appear. There's an icon that looks like a dialog box labeled chat. This is used to join in on the virtual conversation. Once the chat box is clicked, the chat log should appear on the right side of your screen. If you have questions or comments during the presentation, please feel free to type them into the chat box and press enter. If you are experiencing any technical difficulties during the program, please use the chat box to alert me and I will try to address your issue. Also, as far as the questions go, we may not have time to address all questions, but we will do our best to answer them all if we can. So also, I would like to point out a few upcoming programs. So on Monday, October 19th at 2, we have a program called Smarter, Greener, Cleaner, and that's presented by the Earthways Center of the Missouri Botanical Garden. Then on Tuesday, October 20th at 10 a.m., we have a program called Painting with Coffee and Tea, and that is presented by Artist First. And lastly, on Tuesday, October 20th as well, at 7 p.m., we have a program presented by Gateway Greening called Season Extension, Growing Garlic, and Winter Gardening. So please feel free to check out our website, slcl.org, for more information on those programs as well as other upcoming virtual programs. So with all that being said, I am pleased to introduce you to Rose Jansen, and she's with the Academy of Science St. Louis. So thank you, Rose.
Thanks, Denise. Hi, everybody. As Denise said, I'm Rose. I'm with the Academy of Science St. Louis, and we're really pleased to be partners with the St. Louis County Library to bring you tonight's Science in St. Louis seminar, Hubble Highlights. For those of you who aren't familiar with the Academy, I'm going to take just a moment to tell you a little bit about who we are. We're an independent science organization supported entirely through community contributions at events throughout the region and these pandemic days virtually. We connect science in the community through free and or very low-cost public talks, science seminars and workshops, and trips and tours that feature scientists and engineering professionals of both national and international renown. And then in addition to advancing the public understanding of science, it is our mission to inspire the next generation of scientists and science advocates, which we do by offering a full array of free and low-cost opportunities expressly for teens, such as teen science cafes, the STEM Teens Youth Leadership Council, Junior Academy of Science, and the Regional Academy of Science St. Louis Science Fair and Honors Division. You can find more information on Academy events and programs on our community-wide programming by visiting our website at Academy of Science, stl.org, or you may also visit us on Facebook, Instagram, or Twitter. Or before you log off tonight, we'll be providing a survey link in the chat window, and you may leave your email address in the survey if you'd like to receive Academy news of upcoming events and programs. With all of that said, I'm going to introduce tonight's speaker, Mr. Rich Heuermann. Mr. Heuermann earned his undergraduate degree in physics from St. Louis University and his master's of science, also in physics, from the University of Missouri St. Louis. He is currently and has been since 2016 a NASA Jet Propulsion Laboratory Solar System Ambassador, one of a group of people assembled by NASA who receive background information and access to images and information about NASA missions and related topics in astronomy, planetary sciences, and earth science. The ambassadors then present programs and facilitate events across the country for schools, civic groups, and the general public. Prior to his retirement, Mr. Heuermann was for 30 years the administrative officer of the Department of Earth and Planetary Sciences and the outreach program coordinator for the NASA Missouri Space Grant Consortium at Washington University here in St. Louis. As an active member of the St. Louis Astronomical Society and a NASA Solar System Ambassador, he remains involved in astronomy outreach programs, presenting lectures, and conducting star parties, public telescope observing sessions. He has taught evening courses in astronomy and planetary sciences at Washington University and the University of Missouri. Prior to his 30-year stint at Washington University, he served as assistant director of the McDonald Planetarium, also here in St. Louis. So we are very pleased to have him here with us tonight to celebrate the 30th anniversary of the Hubble Space Telescope. He's going to be talking about Hubble highlights, 3 decades of discovery. Won't you please join me in welcoming Mr. Rich Heuermann?
Hi. Let's see if I can get the program up. There we go. Thank you for the introduction, Rose and Denise, and the opportunity to talk to you today about the Hubble Space Telescope. Before we talk about that telescope, that's what we're going to spend the time on. I wanted to make sure that you have heard about the Library Telescope program. Now, you can't really get access directly to the Hubble Space Telescope, although you can see pretty much all of the images. They're posted by NASA online in various places. But you can check out from St. Louis County Libraries, all of the branches, as well as the St. Louis City and St. Charles, many of the municipal libraries like Webster Groves, Kirkwood, University City, and some other libraries in Jefferson County and in southwestern Illinois. You can check a telescope out for a week. If you're an adult, then you can check out a book. So let me show you just for a minute so you get an idea of what it looks like. So this is the telescope that you will be able to use, and it's very portable. It's not heavy. It's easy to work. Basically, you move it up and down and turn it sideways and point at the object at which you want to look in the sky, whether it's planets or the moon, or maybe double stars, binary stars, stars that are in orbit around each other, maybe some star clusters. And the bright stars and the bright star clusters and the planets you can see from the city or from urban locations. There's information with the telescope on how to use it. It has a finding device on it that makes it a lot easier to spot something when you see it in the sky, to get the telescope to look straight at it. It's called a red dot finder. And there's some explanation about how to use that too. There is a constellation book that will help you find your way around the night sky, although it does not list the planets. You would need to look somewhere else, perhaps online, to see where the planets are. I'll tell you right now, Jupiter very bright in the southwestern skies after the sun goes down and the sky gets dark. Saturn above and to the left of that. And then Mars on the other side of the sky toward the east. So it's for the next at least month, it's going to be a prime season for looking at planets. If you're up very early pre-dawn in the morning, you'll see Venus very bright. So that's the Library Telescope program. And if you haven't used a telescope in a long time or ever, then you might want to literally check it out. The other thing I would mention, as part of the St. Louis Astronomical Society, that group meets every month, and now, of course, it has to be by remote control by Zoom. Anyone is welcome to join the meetings. The next one is tomorrow night at 7:30, and the topic is Black Holes, Astrophysics Final Frontier by Dr. Marco Gavaglia of Rolla, University of Missouri Science and Technology. If you want to link up with that, then I just suggest that you search for St. Louis Astronomical Society. That'll give you the website, and there'll be a link on the website to listen and watch Dr. Gavaglia's lecture about black holes. So that's coming up tomorrow. We are here tonight, though, with perhaps arguably the most remarkable, productive, and popular scientific instrument ever devised, and certainly for astronomy, and that's the Hubble Space Telescope. And we're going to take a look at the story of the Space Telescope and how it acts, how it functions, how it got started, and concentrate then on some of the spectacular images from Hubble. And I will tell you that every image that you see that's a Hubble image, you can find on the internet if you just look for them. There's if you, again, Google, just a search on the Hubble Space Telescope, or look at Hubble site, HUBBLESITE.org, I think it is, and other places, they have the images there for you to look at. So 3 decades of discovery, Hubble highlights. Let's see. We begin with the image credits. So trying to give credit where credit is due. These are the places from which I've taken the images that you are about to see. Several NASA sites, scientists from the Space Telescope Science Institute in Greenbelt, Maryland, that operates and manages the Hubble Space Telescope, among other things, under NASA authorizations, and other facilities and individuals that you see there. The story really begins in 1946 when a well-known astronomer at the time, Lyman Spitzer, wrote a scientific paper explaining why a space telescope, a telescope in space, although expensive, would be worthwhile in effort, time, and financial resources. And then a scant, let's see, 44 years later, we have the launch of the Hubble Space Telescope from the Space Shuttle Discovery on April the 24th of 1990. So here is the launch picture, April 24th. It moves into orbit, and on April 25th, the Hubble Space Telescope is deployed. So that thing that you see over here on the left, that's the Canadian arm that gently lifts the telescope from the cargo bay of the space shuttle and then pulls away from it. And then the shuttle pilot very carefully moves the shuttle away, and Hubble is free flying then. The launch and the first operating date, April 25th, 1990. So why do a space telescope? It's very much more expensive than building a telescope, including larger telescopes on the ground. There are 3 primary reasons, and we'll be referring to them as we go along. So let me just mention them now. One of the main reasons is that you're up above the Earth's atmosphere, so the images are not blurred by the air. Now, we think of air on a good day as being clear. And if there's no wind and it's pretty still, then we would just kind of think of it as just being there, see right through it, transparent, no problems. That's not the way it goes. Even clear air has pockets every few inches to every few feet. Pockets of air that are a little bit hotter or cooler or a little bit denser or less dense than the surrounding pockets. And the problem is that when a light beam hits one of those pockets, it's deflected. And then it goes a few inches to a couple feet, and then it hits another pocket and it's deflected again. And that causes the image to blur or shiver. That's what causes the stars to twinkle. That means that you can't get a really clear image from the ground by just looking through a telescope. And the larger the telescope, really the bigger the problem, because you're looking through more pockets. So one of the big advantages of the space telescope is that you don't have this blurring that's caused by the Earth's air, because you're above it. You can also see energies, we can call them colors, by kind of extending what our eyes see, that aren't visible from the ground. But fortunately for us, the ground blocks out a lot of the sun's radiation. The X-rays and most of the ultraviolet rays that are very harmful, also large chunks of the radio waves that the sun emits. And those are all deflected, reflected, absorbed, scattered by the Earth's blanket of air, which is a good thing for living creatures, but it's not a good thing if you want to study, observe the universe in its full being, because you can't see then X-rays and ultraviolet rays and a lot of radio waves. The space telescopes get above the air, and now they can see colors and energies that are not visible from the ground: X-ray, ultraviolet, infrared. Hubble can see ultraviolet, regular visible light, and infrared light. And then, of course, a third advantage, which is known to anybody who's ever tried to be out there with a telescope, there's no problems with the weather. It's always going to be clear because you're above all of the weather. So those are the reasons behind having a space telescope and going through the time, energy, and expense of doing that. Just to give you a picture of what Hubble is like, if you could picture it in your living room, if you have a pretty large living room, it weighs about 12 tons. It's 14 feet in diameter. That is determined by how big the space shuttle's cargo compartment was. 43 feet long for the same reason, limited by the shuttle's cargo space. It's up there at about 335 miles. It's a pretty circular orbit. It just jiggles a couple miles in each direction as it goes around the Earth. And it goes around once about every 95, 96 minutes at 17,000 miles per hour. So the Hubble is up there and it's doing this observing or getting ready to do it at 17,000 miles per hour, 335 miles up. And the scientists, as well as the general public, are waiting for the first pictures. This wasn't the first picture, but it's a good one for the example. The picture on the left, as you see, is a picture that back in 1990 would have been a pretty good result from the ground of the dwarf planet Pluto and its large satellite Charon. Now, Pluto is out there more than 3 billion miles away, and it's only 1,400 miles or so across. It's much smaller than our moon. From the ground, this was the best pictures, pretty much the best picture we could get at the time. Over on the right, you can see that Hubble is a huge improvement. It now splits the picture so that Pluto is clearly separated from Charon. And so that's part of what was trying to get accomplished with this mirror. The mirror, by the way, is about almost 8 feet across, 94 inches. The bad thing is all that blue stuff that you see in here. That is not supposed to be there at all. And that told scientists, astronomers, immediately that there was something badly wrong with the telescope's mirror. And many of you might remember from 30 years ago, the furor that erupted from what looked to be a huge billion-dollar fiasco. So here's Newsweek, billion-dollar blunder. They weren't very kind to NASA. Cartoonists, maybe some of you remember Mr. Magoo, who was the nearsighted guy in one of the cartoons. And it looked like this was going to be a colossal failure of the first degree. Now, NASA never took this stance. You can see from the cartoon caption, maybe outer space really is blurry and out of focus. And NASA never tried to give that as an excuse. NASA knew right away that there was something wrong with the mirror. And it turns out that the mirror was improperly shaped, and it was off by 0.0022 of a millimeter, and a millimeter is the smallest marking line on a meter stick. That's about 1/50th the width of a human hair. But that was enough to destroy the crispness of the image. What to do? Well, one of the things that was built into the Hubble Space Telescope design was the facility to be able to go up there and make repairs and changes, fix things when they break, remove instruments, and replace them with better versions as time went along. all the while 335 miles high, moving at 17,000 miles an hour, using space shuttle astronauts to do that. So much sooner than was anticipated, the first repair mission was put together. And in December of 1993, the shuttle launched with 2 pieces of equipment. And one was a package of optics called COSPAR that corrected for the defects in the mirror. They were able to tell from the ground and from looking at the problem. The problem was actually with the instrument that shaped the mirror in the first place, was that 1/50th of a human hair out of alignment. So they could tell by that exactly how the mirror was distorted, and so they designed optics, a corrective lens package sort of to fix that. And then the other instrument was to replace the wide field camera. And they did that with this camera that you see here in the picture that the astronaut is ready to deploy. You can see it's a very large instrument because they built the correction into the optics of the camera. So December 1993, the first repair mission is accomplished, and we wait to see what kind of images result. And fortunately, the fix was very good. On the left, you see the picture of a spiral galaxy called from a catalog number M100. I'm not sure why my field is jumping like that, with the original flawed optics uncorrected. And on the right, you see the picture with that new camera that you saw the astronaut deploy. So the repairs were very successful. And from December 1993 on, the Hubble telescope was fully capable of doing the jobs for which it was designed. And so now it could read the third line from the bottom. Here are some examples. The planet Jupiter in July of 1994 was hit by a comet. It was actually disintegrated, the comet, on the comet's prior pass by Jupiter, and the pieces then hit Jupiter in July of 1994. And the Hubble Space Telescope was positioned to be able to see that just a few hours after impact. The impact actually occurred on the other side of Jupiter. In visible light, we see holes in the clouds, these dark markings. These you could actually see with small telescopes in the ground. I saw them in a small telescope from Clayton, Missouri, back in July of 1994. This picture shows a lot more detail because it's showing ultraviolet light, the light that makes black lights glow. And it's an example of how you can see more things and understand better what's going on by using energies in invisible light, in this case, ultraviolet light. Another example lies within this giant cloud of dust and gas that you could see with these library telescopes, probably not till about midnight now, but next month at this time, maybe more like 10 o'clock. The nebula in the constellation of Orion the Hunter. It's the middle star in the Hunter's sword. And this is a picture from a large ground-based telescope, although it's a picture that now amateur astronomers are able to to achieve with all the advances in electronics and optics since then. But this is not the picture that you will see with the library telescope. You will be able to see a hazy patch that has the suggestions of this shape, but not the colors that you see here. But with the Hubble, they could zoom in on portions. Here, where it's dark, or is where the dust and gas are the thickest. Here is gas of hydrogen in blue and hydrogen in red and oxygen in blue. And this is starlight reflecting off dust from stars embedded inside. And the dark places are where the dust is too thick for the starlight to get through. And when they zoomed in on it in a picture like this is a little bit hard to see, but this little white speck, when they zoom on it, is revealed as these kinds of shapes. And what we're seeing is gas and dust that's propelled by very hot stars that energize it, heat it up, and then push it out away from the star. And that causes a bow shock here to build up as the gas plows into these little sections of the cloud. And these dense sections are where new stars are being born even today. So they're called proplyds, for protoplanetary disks, and they are a look at stars in formation, which was one of the areas of research for which Hubble was designed. Here's another one. It's actually a collection of, I think it's 24 Hubble images of the remnants of an exploded massive star much bigger than the sun. And the light traveled for 6,500 years through space until it reached the Earth on July the 4th of 1054. And the Chinese astronomers recorded such a thing. It was visible in the daytime for quite a while and visible at night, very bright for months. And it's the exploded debris from a supernova remnant, a massive star that exploded at the end of its lifetime. Now, not only could Hubble show the gas, the intricate deployment of the gas over time, but it could also analyze what the gas and dust left over was made of. So a very quick look at spectroscopy, and that is the science or subscience of analyzing light by breaking it into white light, by breaking it into its component colors. Now, what happens in the laboratory, if you have a gas tube full of hydrogen and you pass it through a prism or another kind of device called a diffraction grating, you see that the light doesn't have all the colors in it. It only has a few, and it has a few very particular colors. Whether you're in St. Louis, Cleveland, or Shanghai, they are always exactly those shades of violet, blue, green, and red. And if you then take a look at mercury gas, then you see other colors different from hydrogen. And if you look at neon, you see another set of colors. So these different colors are essentially optical fingerprints that identify hydrogen, mercury, neon, helium, all of the elements. Each element has its own unique pattern. If you, instead of having a gas that glows, have a gas broken into all of its colors, but with other elements, with some elements present, then you will see a dark line where the bright line was for hydrogen. In all of the places that the hydrogen colors glowed, there are now the absence of those colors in the white gas. And that means by looking at these lines in the spectrum of a star, and here are several different stars, you can tell from where the lines occur, from what the shades of colors are, what the gas is made out of. You can also tell how hot it is. You can tell what the pressure of that gas is. And that's how we can tell the composition and other different parameters from stars, even though we can't get the star stuff into the laboratory. So that's what Hubble could do, and that's what Hubble has done in the case I showed you with that exploded star, the supernova remnant. Here is a giant collection of very, very old stars, 3 times as old as the sun, called a globular cluster. And as Hubble's resolution it had improved so much what was possible from the ground, we're able to look more closely at individual stars, including those toward the center of that globular cluster. Here's another example, a different globular cluster, visible from the southern hemisphere. And this little square, you see from the ground, these stars are so tightly packed that they just wash out the image, and all you see is this white blur. With Hubble's resolution, it can take this section of the globular cluster and zoom in on it to look at individual stars closer to the center. And these that are circled here, so here's a couple examples, were not the way stars were supposed to be. They were expecting red stars, very old stars are going to be red stars, and they found blue ones, so they were called blue stragglers. Hubble was able to map out and detect and look at the spectrum of the blue stragglers and help us figure out that the reason that they are blue is because they are combined stars. Two smaller red stars that over time essentially collided with each other to make one bigger star and turned blue in the process. You need the Hubble resolution to be able to pick out these blue stragglers. Next door to our own Milky Way galaxy, which is a collection of 100 to 300 billion stars, there is a slightly larger galaxy in the constellation of Andromeda, known by the catalog number M31. And from the ground, with a medium-sized telescope, we get a nice image of the whole galaxy. With a large telescope on the ground, then instead of seeing the whole thing, these are 40,000 light years across, we can zoom in on the central core of the galaxy and see the 2,000 light years. Okay, so I have to mention and remind you that a light year is not time, it's a distance. It's the distance that light can travel in a year, traveling at 186,000 miles a second. It travels 6 trillion miles in a year. So the inner 2,000 light years visible from the ground. But with Hubble, we could get down to 40 light years. And we could look at the center of this large spiral galaxies and see two bright spots that turn out to be supermassive black holes. Not a single core black hole. This is the center of the Andromeda galaxy. This brighter one is a supermassive black hole a little bit away from the center. This whole distance now is only 40 light years. So that was not possible to do with the resolution from the ground, with all the blurring. So another example, this beautiful spiral galaxy called M51, which has dense nucleus, tends to be older stars, and then coming out from there, winding around, are the spiral arms where new stars are forming and where dust and gas is concentrated. And this is the view from Hubble in the visible light. And you can see some places here that are kind of red blurs that are clusters of stars that are very, very young, formed, astronomically speaking, fairly recently. On the right is a processed image that shows what you gain from having the ability to see other colors, other energies that our eyes can't see. So this is the result of combining a visible light picture with an infrared light picture from Hubble. So infrared is red that's redder than red. It's too red to energize our eyes to detect. We feel it as heat. And infrared light can pierce the dust and gas that optical light cannot. Optical light is blocked. The infrared light gets through. So what they did with this picture is they combined an optical picture with the infrared picture, and they electronically subtracted the light of the individual stars. And what was left was this curl that followed the spiral arms, but it's made now primarily, or showing primarily the dust and gas, and showing that the clusters of the new stars are forming right along the dust and gas lanes of this huge spiral galaxy. There's another spiral galaxy. This one is 100 million light years away. That's just incredible. The light that got to Hubble, and you can actually see this, I don't know about with the library telescope. I think you probably could, but it would be a tiny faint smudge. But through larger telescopes, including a couple from the St. Louis Astronomical Society. They don't see this level of detail, but they definitely show the disk and spiral structure. Well, the deal with this one from 100 million light years away, Hubble has such a good detail capability that it can zero in on individual stars in this galaxy. Now, you see stars in through here. These are in the Milky Way that just lie between us and the spiral. But there are stars in the spiral, embedded in the spiral, that Hubble could see. And it looked for particular stars, giant yellow stars, 4 to 20 times the mass of the sun, and they're called Cepheid giants, supergiants, massive yellow stars, and they are all of pretty uniform brightness. And so we can tell how bright they are in absolute terms, how absolutely bright they are. We look at the Hubble picture and see how bright they appear. Now, an object that gives off light, as you know, is brighter when you're closer to it, and it gets dimmer as you move farther away. And there is a very simple equation that lets you calculate the distance if you know how bright the object looks and you know how bright it really is. So if you had a 100-watt light bulb, then you would know from the package the bulb came in that was 100 watts. And then if you moved away a mile, you would be able to see how bright it looks like in binoculars or a telescope. And knowing how bright it was, you can measure that with a device called a photometer, among other things. And knowing how bright it really is, the 100 watts, you could tell how far away you were. You could tell that you were the mile away. That's a principle for Hubble's being able to measure the distance across 100 million light years. These distances are not only interesting because they tell us something about what the universe is like far beyond the Milky Way, but they help us measure how fast the universe is expanding. And so this is part of a system that's used to measure distances to farther and farther objects and tell by how fast those objects are moving, how fast the whole universe is expanding. Hubble provided a big leap in the farthest distances that these stars were able to be seen because of its ability to resolve fine detail. This is another kind of a galaxy called an elliptical galaxy, and it's known by its catalog name M87. It's a picture from a ground-based telescope. It's bigger and more massive than Andromeda or the Milky Way. There are maybe 1 trillion stars in this one, which lies in the constellation of Virgo, the Maiden, as seen from the Earth. It's not only this big globe of generally old stars with not much gas and dust left, but we can see that it emits a jet of material. This is a corner of M87, or the central part of M87, and we can see jets of material that have been pushed out at very high speed from both sides. You can't really see the other side. It's moving away from us, kind of lost in the glare. And with Hubble, we could even see how those jets changed over the course of time from 1999 to 2006. So we're watching this high-speed gas ejected from the old, huge elliptical galaxy move through space, smack into the very thin gas that lies beyond the galaxies and between the galaxies, and heat that gas up, cause it to glow, and we can follow the passage of the jet over time using Hubble's resolution. Now, the jets, we now know, were expelled, pushed out, ejected by a supermassive black hole in the center of M87. The most famous science image of 2019 was this image built up by 7 radio telescopes scattered all over the world of the central black hole in this M87 giant galaxy. And what we're really seeing is the shadow of the black hole. and very hot material that's being pulled in by the very strong gravity of the supermassive black hole. And in being pulled in, it's speeded up and by friction glows at very high temperatures. Again, one of the strengths of the Hubble design was that the telescope could be serviced over the years, and we had the unplanned servicing already in 1993 with the corrective optics and the replacement of the wide field camera. There were other missions, as you can see. There was a second servicing mission in 1997. It changed out some instruments with put improved instruments in that improved the resolution and the capability to tell the colors and compositions even more. Then in 1999, they actually hadn't planned the third mission to be in 99. It was supposed to be in the early 2000s, but Hubble is guided and stabilized with gyroscopes and something called reaction wheels. And the problem was that some of the gyros were failing after this 9 years in space in constant use. If they lose one gyro, they can still manipulate and aim Hubble. But if they lose a second gyro, they have real problems in controlling the telescope. So they couldn't wait for the planned time frame. They had to break that third mission up, and the first part of it went up. Then in December of 1999, it put new gyros in, it upgraded the computer system, and it replaced a fine guidance sensor, which is a very high resolution telescope, a small one, on the built into Hubble that helps it acquire the images that it needs to find. And then in 2002, it finished the third mission by putting in other instruments, changing out the power system, and putting in new solar panels. It's solar powered here, and the new panels were smaller and more efficient, and they didn't flutter as much as the Hubble moved around the Earth. So that was an improvement also that improved still further the resolution. Now there was a fourth mission that was planned, but the second space shuttle tragedy happened in 2006, and NASA determined that it was too dangerous to go to Hubble again to do the final repair mission. And so they were going to decommission the telescope when the gyros failed and the electronics failed. Now, the scientists, everybody wants to use Hubble, and there are hundreds of teams of scientists who have used it in its history. And so they were lobbying very hard to get that shuttle mission, that last repair mission going. And the general public was lobbying hard because they had seen these wonderful images from Hubble over the prior 12 years. So NASA figured out a way to do this. See, the problem is, if the shuttle goes up to Hubble to repair it, but then develops a problem on orbit such that it would not be safe to land, it would be stranded, it would be marooned in space. It cannot get to the International Space Station. The International Space Station has a slightly lower orbit, but much more problematic. The orbit is at a different angle, and these things are moving, both of them, at 17,000 miles an hour. So they just don't have the fuel capability to radically change the orbit of the shuttle to get from Hubble down to the space station. It's not possible to do that. After a lot of planning and consideration, NASA figured out a way to get that last repair mission in. And the solution was to get a shuttle loaded with the new instruments and the upgraded electronics and the gyros and the batteries, and launch it to Hubble with another shuttle fully fueled and ready to go to rescue the first crew if their shuttle developed fatal problems. And that's how they were able to do, finally, the last mission. And that was the last time that we've been up there to service Hubble, was back in 2009. Was the last batch of new instruments It was new batteries, it was new gyros, it was a refigured telescope. When they were done in 2009, that almost 20-year-old telescope was a much better instrument than it was in 1993 when it was repaired. Not going to read through all of this, but with the repaired instruments and the improved instruments and the repaired and upgraded electronics and batteries, it's an indication there were certain things that they wanted Hubble to do and investigate. And Hubble indeed did these kinds of things. How big the universe is, what galaxies are made of, the gases inside and outside of them, the origin and evolution of the solar system, supermassive black holes. These are a very small list of other things that Hubble discovered that scientists had no idea Hubble would be able to find and do when the telescope was designed and launched. And so over this now 30 years, Hubble has been in the forefront of virtually all sections of astronomy and many sections of planetary sciences. It's not only what the original idea was, it's all the things that we found out during the course of the time that we've had Hubble functioning. One example is looking for planets around other stars. That wasn't even considered when the telescope was designed in the 80s. Here's an example from a bright star. You can see it in the night sky tonight if you know where to look in the south, called Fomalhaut. Hubble images. It was known from ground-based telescope that there is a disk of gas, a thin disk around the star. And it was speculated that that gas and dust could be a precursor to planets forming around this bright star. Hubble images in 2004 and 2006 showed a section here out of all of this stuff, all of this detail, that moved a distance in 2 years consistent with it being in orbit around the central star. There is a star here. The devices to block out electronically the central star so that the starlight doesn't swamp out the disk light. So the little dot moved in such a fashion as to be consistent with something in orbit around the central star. That is a planet. And so it was thought that this was the first visible detection, direct imaging of a planet around a different star. We've detected, now it's up to over 5,000 planets around other stars, but very few have been able to be seen directly and imaged. The rest of them are seen indirectly by their effect on the star. Now there is some question that this might not be a planet forming after all, that it might be the result of a collision of smaller things like asteroids out there around Fomalhaut that created a big dust and gas pocket that might be slowly dissipating. But there are other exoplanets that have been imaged, not only by Hubble now, but also by the greatly improved and much larger telescopes on the ground. One of these other exoplanets, Hubble was able to analyze the light and detect a lot more water vapor in the atmosphere. So it was able to see what the air on this giant planet orbiting very close to a distant star was able to see what the atmosphere, what the air was made out of. It's part of the search for exoplanets, particularly for planets that are more Earth-like, with the hopes that we could get to the point where we can find an Earth-like planet in a zone where water can be liquid on the surface and where life may have developed in other places. Well, back from the 20th anniversary, here's the cartoon with Hubble looking out into the universe, and the question coming from the ground, maybe it's time to point it toward the Earth to search for intelligent life? And I'll leave that question up to you to ponder as you look around what goes on in the world today. But I'll also tell you that it's not really a good cartoon, because Hubble actually looks at the Earth more than it looks at anything else. It continuously or frequently looks back down at the Earth to help calibrate the instruments, and then back out at the sky again. But maybe it should be searching, looking for intelligent life. Okay, we're going to move on as we near to some more of these Hubble images. This is a mosaic of stars looking in toward the center of the Milky Way galaxy, the galaxy that the sun is one of 100 to 300 billion stars orbiting around the center of it. And you can see it's just packed. And you can see color, and they're real color. Colors tell us how hot the surface of the star is. The red ones are cooler, the blue ones are the hottest ones. Hubble, in looking at those spectra, breaking the light into the colors, can tell that there are two kinds of stars, general kinds of stars called populations, depending on how much material they have as a percentage of their makeup that is not hydrogen and helium. So there are some that have a lot more carbon and nitrogen and oxygen and lead and other elements besides hydrogen and helium. And the ones that have the least are the oldest stars. And the ones that have more have these additional heavier elements because they were produced in an early generation of stars. Perhaps the single image of the greatest impact is this image of a tiny spot near the Big Dipper in the sky that was chosen in 1995 at the end of the year in December because it looked like it was empty. And the idea was to turn the most powerful telescope that we had, the one that was able to see the farthest, the Hubble Space Telescope, at an empty spot in space. Well, given how hard it is to get time on the Hubble telescope, this seems like a strange thing to do. But they spent 100 hours in the month of December 1995 on this, what looked to be an empty spot in space. And they figured that they would probably find a few galaxies there, and that might help them estimate how many galaxies there are in the whole universe. Well, they found more than a few. They found over 3,000 images in this tiny portion of the sky. This is called the Hubble Deep Field. The dots that you see are all galaxies. The closer ones, the bigger ones are closer ones. The tiny little dots are galaxies farthest away, and that means the galaxies whose light is reaching us from older and older periods of time, back over 10 billion years out of the universe's total 13.8 billion years. And by looking at how many galaxies there are and how old they are and how far away they are, we get a picture not only of how many galaxies are in the universe, but how they have changed over time. The ones that are very far away aren't the spirals and the giant ellipticals. They're smaller galaxies. We think that the galaxies that we see easily today that are only a few 100 million light years away are made up of many, many smaller galaxies that have collided and merged over time. So that's a Hubble Deep Field. It was such a powerful thing that for research that they did another deep field image in the southern hemisphere to see, did they happen to hit a busy spot in space? And it turns out, no, the southern deep field was also full of thousands of galaxies. And they repeated this again in 2004 and 2009, and they did one of these deep fields in infrared light, they did one in ultraviolet light, and then they finally combined electronically the images and information from all of these pictures into one extreme deep field that is one of the probes that we have now for looking back into time to see how the universe evolved and developed, the visible universe. Preview of coming attractions. We hope Hubble will last still for several more years. Remember, that last repair mission was all the way back in 2009, so it's already gone 11 years. The next giant space telescope is the James Webb Space Telescope, the sort of successor. This one is radically different from what Hubble is like, and hopefully will be as productive. It doesn't look at light that we can see, invisible light. It looks only in infrared, in heat kinds of radiation. Its mirror is 21 feet across, where Hubble's is just under 8 feet across. It's so big that it can't be launched as a mirror intact. It has 18 separate segments that have to be assembled in space to make the mirror. The infrared capability means it has to be shielded from heat, not only from the sun, but also from the earth. And so it has this elaborate multi-layer heat shield to protect the telescope. It's looking at objects emitting heat, and they would be swamped out or drowned out in the glare of the sun and the earth if the telescope weren't shielded. It's also cooled. It operates at 370 degrees below zero. Your comparison for sizes and showing that it operates in the infrared, not in the visible. Well, launching this is going to be a challenge because the heat shield has to be assembled, multi-layer, and the telescope has to be assembled. And this is all going to happen over almost 1 million miles away from the Earth, in a zone where the gravity of the Earth and the gravity of the sun are about the same strength. It's called the L2 Lagrangian point. That means it has to be assembled robotically, and it cannot be serviced. We can't get out there if something should go wrong. Here is the full-scale mock-up of the James Webb in front of the building in Greenbelt that houses Maryland, that houses the Space Telescope Science Institute. And here is the team just at Greenbelt that's been working on the James Webb Space Telescope. The Webb is now scheduled to launch on Halloween next year, 2021. It's been years delayed due to technical problems of different kinds. The mirror was actually assembled and tested in 2016. But there are a lot of problems testing and getting a reliable monster heat shield, multi-layer heat shield, as well as the different components of the telescope. It's also been slowed, of course, by the COVID crisis, pandemic. So now the target date is October of 2021 to go up there and first supplement or expand the capabilities of Hubble in the infrared. That will let us see back almost as far as we can see in the infrared through the dust and the gas, and it will also penetrate the dust and the gas in the star-forming regions to give us close-up views of new stars forming. For the rest of the time, I just want to show you some of these magnificent images from Hubble. This one is a section of the cloud in Eta Carina, and just swirls of dust and gas, new stars embedded within. Here's one section of that where the radiation, the heat, the light, the energy from forming powerful new stars embedded in the dust and gas is pushing away and sculpting into these fantastic shapes the dust cloud from which it is forming. Here is a Hubble view. These are all going to be Hubble views of a new star cluster, relatively young stars, only a few tens of millions of years old. and they have hollowed out the dust cloud from which they formed. Here is a section of a dust cloud in the Large Magellanic Cloud called the Tarantula Nebula, and it's a mosaic. It's an extended star factory, and they found over 800,000 new stars forming in this galaxy, an irregular shaped galaxy near the Milky Way. It's only about 170,000 light years away. Within our own galaxy, in the constellation of Orion, near one of the stars in its belt, is the Horsehead Nebula that you may have seen pictures of. Here's a picture from the ground with a telescope that's 3 feet across at Kitt Peak. And here is a Hubble close-up that shows much better picture of the cloud and the stars that are embedded within it. And this is in the visible light. We can go to the infrared picture, pierce a lot of that dust and gas, and see brilliant young stars that you could not see here, that are stars just forming in the Horsehead Nebula. Instead of these giant clouds from which new stars form, there are some small clouds that are the debris of stars in their approaching their last stage of evolution. They're called planetary nebulae because in earlier telescopes, some of them were roundish and sort of look like planets, but they're not planets. They're 20 to 40% of the gas in a star that was expelled as the star aged in one of its last stages of evolution. So there is a dying star in the center here. This is nicknamed the Butterfly Nebula. The gas was pushed out for some reason in 2 different directions to form this image. This one is called the Cat's Eye. And here we can see where there were multiple expulsions of gas from the star. This one is the Hourglass, again with multiple emissions of the outer atmosphere along 2 different directions. If we're back to the giant dust clouds, this is one of the most familiar, the most iconic of the Hubble pictures, the Pillars of Creation, a section of the Serpens Nebula. It was again imaged, and that was back in what, 1995, I think it was. Oops. Doesn't want to go that way. Yeah, 1995. In 2015, with the improved optics, they looked at it again and got this even more spectacular image of the eagle. Again, being sculpted by the brand new stars buried within, just forming within the depths of the thickest dust and gas clouds. And here's an infrared picture that shows that, piercing the dust and gas to reveal some shadowing and some central dust and just thousands of new stars in formation here. There's another star cluster that we can see, the center of another globular cluster, the very, very old stars, not the new stars. Spiral galaxies that are just gorgeous, with the central region and then the spiral arms of dust and gas where new stars are forming, coming off of the central core. And the spiral arms take somewhat different shapes. Some of them are tighter wound, some of them are looser. There are some, and the Milky Way is one of those, that don't just have an elliptical core, but a bar of older stars in the center from which the spiral arms are emitted. There are others that are not like the ellipticals and not like the spirals or the barred spirals. They're kind of irregular in shape. This one's nicknamed the Cigar Galaxy. It's near the Big Dipper. You can see it. You would be able to see it in the library telescopes if you went way out where it was dark. You would see this bright part of it as an elongated, as sort of a streak. You wouldn't see this part. This is gas that's being expelled from the center of this galaxy, which is known by its catalog number M82, or it's nicknamed the Cigar Galaxy. For some reason, I get that. Try this again. Here we go. we see other galaxies that are irregular in shape because they've been distorted. The gravity of a nearby galaxy has pulled, pushed, and twisted, in this case, a spiral galaxy to this shape here. It's called the porpoise because it's imagined to look like a dolphin. I think of it as a hummingbird as well. You can see how the spiral dust and gas arms have been stretched out and twisted and turned by this more massive galaxy nearby. The interacting galaxies, some of them pass right through one another because the separation and distance between individual stars is so great, and you get these unusual formations here between these two big ones and smaller one up here. You get peculiar formations like this ring galaxy. It's not possible to form a ring of stars like this on a galactic scale in isolation. So it was probably a spiral galaxy that was distorted by having this other galaxy kind of zip right through it. Zip meaning, oh, only several 100 million to 1 billion years or so to go on through out the other side and in some cases come back again. Now, these colliding galaxies are of more interest than just curiosities. Here's an artist's conception of the Andromeda galaxy that we saw before and our own Milky Way only 5 billion years from now. They're on a collision course. They'll first pass nearby and through each other, and then as their mutual gravity pulls them in, make several passes and then merge into one super galaxy. So that's our future in the distance, in the way distance. We don't know what will happen to the sun and the planets. We don't know if they'll be absorbed into the super galaxy or if they will be gravitationally flung out into empty space. At 5 billion years, this will be a very, very old sun getting ready for its last stages of evolution. This is the farewell picture in 2009 from the Space Shuttle repair mission as it left the Hubble in orbit, fully repaired and upgraded and ready to function as it has now for an additional 11 years and hopefully for a few years anyway still to come, hopefully at least 5 or 6. I don't know about a decade. It still finds things all of the time, not only in the distance, not only mapping out the expansion of the galaxy, but here in our own solar system. And this is an image of asteroid 6478 Gault that was taken just a year or two ago. And it looks like a comet, but it isn't. It's a rocky, icy asteroid, and the sunlight has caused it shining on a surface that has bright and dark areas to it, shining unevenly in that sense. The dark areas are going to absorb more sunlight, of course, causes it to spin and spin up faster and faster. We estimate that it gains a whole second every 10,000 years. Yeah, but over millions of years, it makes a difference. And so now it's spinning fast enough that it's actually throwing material off to make a tail like this. I hope some of you got a chance to see this comet earlier this summer, Neowise. Here is a picture with Stonehenge in the foreground and the comet in the background. I went out to a site that the Astronomical Society uses with some of the astronomers as well, the amateur astronomers, and this is pretty much what we saw when the sky got dark. It was just gorgeous. Tried to look from the city and it was so faint that even through the telescope, wasn't able to see it very well. It's fairly close to the horizon, moving around the Big Dipper over the course of several weeks. So this was Neowise. Well, Hubble was able to zero in on a tiny portion. Here's the big long tail, and in the front part of the comet is a piece called a coma that is a ball of dust and gas about 11,000 miles across. And what happens is that the sunlight heats this up and pushes the gas and dust backwards away from the sun direction to form the tail. There's a nucleus that contains the ice and the rock that is the real guts of the comet, that's only 3 miles across. And even Hubble can't see that kind of detail from a distance of 27 million miles. But it did give us a view of the coma, the central regions here, and we're able to discern a couple of jets being expelled as the surface gets heated and the ice changes to gas, sublimates, and then erupts from the surface. So that is an image from just this August by Hubble. So what will Hubble find in the future for its remaining years? Your guess is as good as the best astrophysicists, the best cosmologists, and the best planetary scientists. You look into the crystal ball, and considering the tremendous discoveries that Hubble has made over the past years, we can only imagine what it's going to find for its remaining time. There are more things in heaven and earth, Horatio, that are dreamt of in your philosophy. And so that's what we have to look forward to as we've looked over the Hubble highlights from 3 decades of discovery. If you have questions, I'd be glad to try to answer them. Let's see.
Well, thank you so much, Rich. I'll go ahead and go through some of these questions. And folks, we are posting a survey link in the chat window. It's from Natalie Bachman, so it's up there now. So if you want to take some time to fill that out and let us know what you thought, you can also leave your email address in the survey if you're interested in receiving e-news on upcoming events from the Academy of Science. And then one of the first questions I think we had is, let's see.
It looks like, what does the dust consist of?
Yep.
I'm sorry, did you have a question?
Yep.
Oh.
So we had a panelist not a panelist, I'm sorry, we had an attendee who had a question, what does the dust consist of, or what does dust consist of?
Yeah. So most of the universe is made out of gas. It's hydrogen and helium. And from the Big Bang, it was roughly 75% hydrogen and the rest helium is by mass, by weight. And then just a tiny percentage of lithium and almost nothing of beryllium or any of the heavier elements. So that was the original gas. Now, over time, as stars formed in their hearts, they smashed together their hydrogen to form helium. And then in another stage of their evolution, they smashed the helium to form carbon and nitrogen and oxygen. In other words, they are powered by nuclear energy reactions. And as the stars get more massive, then they can make more and more different kinds of elements as they go through later stages of their life. The sun is big enough to fuse the helium into carbon, nitrogen, and oxygen, but not to go much farther. But the stars, and they're very rare, but the stars that are bigger than the sun go on and form even heavier elements. Then when those stars end their life, they do so explosively, like that one picture that we saw earlier of the Crab Nebula. Stars like the sun don't explode, but they make those planetary nebulae, and they push out the gas and the heavier particles that they have manufactured in their hearts. And that is the dust part of it. Carbon and oxygen, there's a lot of nitrogen there. Those are the primary constituents. But then there are smaller amounts of other elements, including lead and iron. And we think from something called a neutron star, an ultra-condensed remnant of the explosion of a massive star. A collision of those produces the gold, most of the gold in the universe. So that dust is literally stardust. It's pieces manufactured in the hearts of very massive stars in the past, or sun-like stars all through time.
Great, thank you. Let's see. Where can the participants see a recording of this?
I'm sorry, where what?
Oh, I think this might be a question for Rose, but where can we access the recording of this?
No.
So I actually put that up in the chat window as well. So you'll be able to see a recording of this talk on the Academy's YouTube channel at Academy of Science STL.
Great, thank you.
Might take a couple days before it's up.
Awesome. Let's see. Who is James Webb's? Pardon me. Who is James Webb, and how did the images go to Earth?
James Webb was the chief NASA administrator some decades ago, and I don't remember exactly the era anymore. I'm sorry, one would have to look that up. But the telescope was named for him in honor of the work that he did for an extended period of time while he was the head of NASA. And out from 1 million miles away from the Earth, almost, the Webb will beam back information the same way that the Hubble does, the same way that the New Horizons did from 3 billion plus miles away when it went by Pluto. The images are, the light goes into the Webb telescope and it goes to one of the instruments where it either forms an image or the light is spread out to form that spectrum so that we can tell what the composition is. And then that is scanned. It's an electronic digital image in some ways similar to what your cameras do. And then that digital image it's broken up into tiny pieces called pixels or pixel elements, and they are different brightnesses. And those brightnesses are changed into numbers that are streamed back to the Earth to giant radio telescopes around the globe that receive the data, and then we can reconstruct what the image was or what the spectrum was. By putting filters in front of the camera, whether it's Hubble or the Webb, we can get an image in, let's pick Hubble because it's easier to visualize. An image in blue, an image in green, an image in red, and combine them to get a true color image if we're shooting for true color. In Webb, it will be images in these different slices of infrared heat that we can then put together and translate into colors that we can see. Then the numbers are beamed down to the ground, they're received, they're recorded, they go through the reverse process where a picture is built up from this stream of numbers that represent the brightnesses, and then combined if they're doing a color picture to make the final result.
Thank you. Let's see. Can research astronomers at university apply to commandeer Hubble, or does NASA set all coordinates for observations?
The time on Hubble is determined by a panel of scientists who receive research proposals from all over the world. And they have to evaluate the proposal, look at how much time is required, try to assess the scientific merit, and then figure out how to allocate the time. In addition, there's a block of time that's reserved for the director of the Space Telescope Institute. And at his discretion, he can get different research projects, get time on Hubble for different research projects. It was his discretionary time that was used for that Hubble ultra deep field that I talked about. So it's a panel of scientists, not determined by a NASA administrator, but by that group that apportions the time on Hubble out. And then they figure out the schedule so they can efficiently move from one object to another.
Thank you. Let's see. What are some stars that we can see now this time of season?
What are some stars that we can kind of see?
What are some stars that we can see currently?
Oh, currently. If you go outside as soon as it's dark and look overhead, then you will see the 3 stars of the summer triangle. So that's not a constellation, it's an asterism. The star that is the farthest to the west. If you look soon enough, then the brightest star of the triangle is almost overhead. If you look a little later, then it's drifted toward the west as the sky shifts. So of the 3 stars, the one that's farthest to the west is a bright star called Vega. It's the brightest of the 3. It's bigger and bluer than the sun, but it's bright because it's relatively close. It's only 25 light years away. Then the next star toward the east is called Deneb, and that's a supergiant white star that's in the tail of Cygnus the Swan. That one is 1,500 light years away. That light that you could have seen tonight if the clouds weren't in the way took 1,500 years to get here. And then the star toward the south is called Altair. That one is 17 light years away. So they make up the summer triangle. Each is in a different constellation. Deneb, as I said, is the tail of Cygnus the Swan. Altair is in the shoulders and neck of Aquila the eagle. And Vega is the shoulder rest for Lyra the harp. Then the bright things that you'll see in the southwest sky are Jupiter. Above and to the left will be Saturn. So that'll give you a start. If the sky is not super bright, then if you look toward the east, you can see fainter stars, a big square that is the body of Pegasus the flying horse. It's upside down and it's only the front half of the horse.
Thank you.
Let me also say that there are different places you can go for this, but one place to get a chart of the sky to see what the bright stars are, skymaps.com, SKYMAPS.com. It's a commercial site, but the sky maps for the month are free. You just download them.
Very cool. Thanks for the tip.
Yeah.
Let's see. Oh, I just lost the, oh, here we go. What is the resolution in arc seconds of Hubble?
Oh, I should know this. I thought it was 1/10 of an arc second. Let me see. First, let me say that resolution is measured as an angle in the sky, yeah? So 360 degrees, as you know, is a circle. And on the sky, if you go from the horizon to overhead, that's 90 degrees. It's a quarter of the circle. Then you go the rest of the way the other horizon, and then you got to go underneath the earth for the other half of the sky. So a degree is 1/60th of the circle. So an arc minute is 1/60th of a degree, and an arc second is 1/60th of a minute. And so 1/10 of an arc second, what is that? Is 1/36,000th of of a circle. And Hubble resolution, I don't know if I can find that in the notes or not. Webb is going to be 1/10 of an arc second. I remember seeing that in review, and I'm not sure enough about Hubble to tell if it's even better than that. I'm sure it's at least that. Well, I got this whole pile of statistics, but I'm not seeing resolution among them.
I wonder if
Yeah, if you'd like to try a different question, if I can spot it while I'm kind of scanning around here, then I'll cut back with it.
Sure. Let's see. How many functioning gyros does Hubble still have? Does it use reaction control thrusters, or is it only rotated by gyros?
As far as I know, all 3 gyros are still functioning. I haven't heard that one has gone down yet. It's possible that it could, but I haven't heard about it. It uses the gyros and it uses something called reaction wheels. They're not thrusters. A reaction thruster uses jets of gas and pushes the gas pushes one way and pushes out one way and pushes Hubble in the other direction. And they don't use that, so they don't have to worry about the gas being used up. A reaction wheel is a little trickier thing. It's a rotating wheel of metal that's hooked up in such a way that if you push on it a little bit, it develops a sideways pull or a torque, and that can be used to move the Hubble very slightly. Now, the good news is it's up there in microgravity where it's just falling around the Earth, so it's not as hard to move a 12-ton telescope as you might think. But the reaction wheels are enough to jiggle it enough to do that, and then the gyros as well. As far as I know, all the reaction wheels and all the gyros are still functioning. You might be able to look at the Hubble site if they have a status portion on that to see. And it needs 2 of the 3 gyros. I think it's 3. It might even be 4. There might be a 4th backup one. I'm not sure if I could find that right away either. It needs at least 2.
So it looks like one of the, I don't know why my audio is being weird. My apologies for that. Looks like one of the attendees noted that Hubble is 0.048 arc seconds.
Okay, so not 0.1, but 0.048. So even better.
All right.
A little bit under 5/100ths of a degree instead of a 10th of, not a degree, an arc second.
Well, thank you so much. This was a really fascinating program. I loved seeing all the images. And thank you to all the attendees as well. I hope that you enjoyed this program as much as I did. So thank you very much to Rose and Natalie for collaborating with the library and to bring the Science in St. Louis programs back to our patrons. Please mark your calendars for our next Science in St. Louis. It will be taking place virtually as well on Wednesday, November 11th at 7:00 p.m. And that's going to be all about drinking as a living system. So it should be very interesting as well. And you can also register for that on our website at slcl.org. Rose or Natalie, is there anything that you would like to add?
Yep, I'll just add real quick that it's about the talk on the 11th is about drinking water, so potable water as a living system, not actually, drinking. So, yep. And Rich, thank you so much. You're always a fantastic speaker, and we have more questions than could be answered. So we appreciate your taking the time to do this evening.
You're welcome. It's a great story. I'm glad if you liked it.
It is.
Thank you very much and hope to see you all on November 11th. Have a great evening.
Bye, everybody.